Welcome to this explainer. Today, we're breaking down the ultimate biological machine, the one keeping you alive right this very second. We're going to dive deep into the exact mechanical, electrical, and biophysical principles that keep your blood circulating day in and day out.
Just to wrap our heads around the sheer scale of this system, think about this. Even when you're completely at rest, your heart is pumping about 5.25 liters of blood every single minute. That is a massive volume of fluid moving through your body, and it does all of this completely automatically. You literally never even have to think about it.
Okay, let's get right into it. Here's our roadmap for today. We'll cover the transport grid, anatomy of the pump, the electrical grid, the mechanical beat, circulation biophysics, and finally, we'll put it all together to solve a real-world clinical mystery.
All right, starting with Section 1, the transport grid, covering both systemic and pulmonary circulation.
What's really fascinating here is how the heart operates as this incredible dual-sided muscular pump. You don't just have one simple loop, you actually have two consecutive circuits running at the exact same time. The right side of your heart is continuously driving deoxygenated blood over to the lungs, while the left side is simultaneously blasting that newly oxygenated blood out to the rest of your body. It's just a highly efficient closed-loop delivery and waste removal network.
Moving on to Section 2, anatomy of the pump. Let's look at the actual hardware of the heart.
Now, the wall of this biological pump isn't just one simple piece of muscle. It actually breaks down into three main layers. The outermost protective layer is called the epicardium. Just inside that is the myocardium. This is the thick, striated cardiac muscle that really does all the heavy lifting. And finally, the smooth inner lining is the endocardium. The whole shebang is neatly enclosed in a protective double-walled pericardial sac, which even contains a little bit of lubricating fluid, so there's absolutely no friction when it beats.
So to keep that massive volume of blood moving strictly in one direction, the heart relies on two totally distinct sets of one-way doors. You've got your atrioventricular, or AV valves, which separate the atria from the ventricles, and then your semilunar valves, at the exits of the ventricles. But here's the crucial part. These valves don't have their own little motors. They open and close entirely based on pressure gradients. If the pressure behind the valve is greater than the pressure in front, boom, it pops open. If the pressure in front is higher, it snaps shut, perfectly preventing any backward flow.
Up next is Section 3, the electrical grid. Because, of course, a pump is pretty useless without power. Your heart actually has its very own built-in electrical wiring, and the impulses trace a highly precise pathway. They kick off at the SA node, which is your natural pacemaker, and travel right down to the AV node. And this right here perfectly illustrates a huge physiological safety mechanism. The AV node introduces a deliberate 0.09-second delay. It acts exactly like a traffic light. It makes absolutely sure the atria have completely emptied and the ventricles are fully loaded with blood before the signal races down the bundle of His and into the Purkinje fibers to trigger that main contraction.
If we zoom way in on those contractile cells microscopically, their electrical action potential looks very different from a standard nerve cell. There's this absolutely critical plateau phase, that's phase 2. This plateau is driven by the opening of L-type voltage-gated calcium channels. So why does this matter? Well, this influx of calcium creates a prolonged contraction and totally prevents your heart muscle from experiencing tetanic contraction. Basically, it keeps your heart from seizing up into a permanent state of cramp. Pretty important, right?
When we measure these invisible electrical signals on the skin using an ECG, we get that classic heartbeat line we've all seen a million times. That sharp spike right in the middle, known as the QRS complex, vividly illustrates the massive electrical discharge firing through the ventricles. In a healthy system, this huge electrical wave completes its entire journey in just 0.06 to 0.10 seconds. It's incredibly fast.
Which brings us to Section 4, the mechanical beat, also known as the cardiac cycle.
We're all familiar with that classic lub-dub sound of a heartbeat. But what's really fascinating is that you aren't actually hearing the heart muscle contract at all. That sound is purely mechanical. The lub, or S1, is the physical slamming shut of the AV valves the very second the ventricles start to squeeze. The dub, or S2, is the immediate slamming shut of the semilunar valves right after the blood is ejected. You are literally just listening to the biological doors of your heart snapping shut under high pressure.
Moving to Section 5, circulation biophysics, looking at pressure and resistance.
Out in the systemic circulation, blood flow is governed by something called Poiseuille's law.
This principle explains that vascular resistance really depends on the viscosity of your blood, the length of your vessels, and, most importantly, the radius of those vessels. And honestly, it reveals a mathematical reality about your internal plumbing that is just astonishing.
Because the radius is raised to the fourth power in the equation, if a blood vessel's radius is merely halved, let's say due to vasoconstriction or maybe some plaque buildup, its resistance doesn't just double, it jumps a staggering 16-fold. No joke. This massive spike in resistance can nearly choke off flow entirely, which means your heart is going to have to work exponentially harder just to push blood through.
To adapt to these immense and constantly changing plumbing pressures, your heart relies on three major determinants of stroke volume: preload, contractility, and afterload. A huge mechanism to understand here is the Frank-Starling law. It basically dictates that an increased stretch on the heart muscle from incoming venous blood automatically triggers a much stronger contraction. So your heart is naturally adjusting its power output beat by beat to make sure blood never pulls up in the system.
And finally, Section 6. Solving a clinical mystery. Let's see how all this looks in a diagnostic application.
Let's consider this exact clinical scenario. A 62-year-old patient presents in the clinic complaining of shortness of breath. Their blood pressure is incredibly high, hitting 70/100. Their resting heart rate is racing at 110 beats per minute, and their ECG shows an abnormally prolonged QRS duration of 0.14 seconds. So, based on all the physiology we've just covered, what exactly is going wrong with this biological machine?
Well, if we step through the diagnosis, we can see a whole cascade of failures. First, their mean arterial pressure is sitting at a dangerously high 123. Second, that prolonged QRS of 0.14 seconds tells us there's a bundle branch block, meaning the electrical grid is totally failing to synchronize. And finally, that massive arterial pressure of 170 creates this immense afterload. The poor left ventricle is exhausting almost all its energy just trying to pop the aortic valve open, which severely reduces blood flow.
Now, in a perfectly healthy system, stretch-sensitive baroreceptors would immediately detect this extreme pressure. They'd instantly trigger the brain to slow the heart rate down via the vagus nerve and dilate the blood vessels. The body is desperately trying to autocorrect. But in our patient's case, this compensatory reflex is failing, and that's exactly what's leading to their acute symptoms.
As we wrap up this explainer, I really want you to take a second and think about the sheer complexity of what's happening inside your chest right now. From the calcium ion channels holding off muscle cramps, to that incredibly precise 0.09-second delay at the AV noder, all the way to the fluid dynamics of Pouzwell's law. Honestly, isn't it absolutely incredible to think about the thousands of silent, automatic calculations your biological machine is flawlessly executing right at this very second just to keep your blood flowing?